To Lecture 24, Part B of the Sturm-Liouville problem, we'll be looking at the comparison theorems. Okay, so before we look at the comparison theorems applied to the Sturm-Liouville problem, we're going to look at comparison theorems in general. And what they are is they basically compare two different first-order equations with various functions on the right-hand side. So to see what this is, let us suppose f and g are continuous in a region, a subregion of R2. Okay, and that f of x and y is always greater than or equals to g of x and y on the same region. Okay, and then if there exists a function y and a function z of x such that their derivatives are defined by the field specified by f and g respectively, okay, on x in AB. And furthermore, if the initial condition of y at the boundary A is greater than the initial condition of z at the boundary A, then it guarantees the fact that y of x is greater than z of x in the whole domain. So briefly, or sort of a quick way of looking at this, it basically states that suppose you have somebody running with a certain velocity, say a rabbit, and we know that if you compare the velocity function at the same position and the same value for y, okay, with the velocity function of another thing that's running with a speed, say a tortoise, and this f is always greater than g, and the rabbit starts in front of the tortoise will never catch the rabbit. Okay, so that's basically what this comparison theorem states, and what we're going to do now is prove it rigorously. So let us say, let g be the difference between z of x and y of x, okay? And we know, at least initially, z of x minus y of x is less than or equals to 0. Okay, and then the derivative of g is equals to basically the derivative of z, which is just g evaluated x comma z of x, minus the derivative of y, which is just f evaluated at x comma y. So it's f evaluated x, but here we've replaced y with z of x minus g of x. Okay, so you cannot immediately say that g of x is negative, because these two functions are evaluated at different points. So that's what makes the theorem a little bit tricky. So what we basically want to prove is that g of x remains less than or equals to 0 for all x. And we're going to do it once again by contradiction. So suppose there exists a c in the region AB such that g of c is greater than 0. And let us then make the set S such that x is in AC and g of x is less than or equals to 0. In other words, we want to look at the set where g of x behaves in the way that we want to prove. Okay, in other words, that condition is true. We've assumed that it isn't true over the whole domain, so we want to find, in some sense, the biggest set where x is less than c, such that this thing is true. Okay, so the first thing is we know the set's not empty because A is in that set. But we also know that the set, by this assumption, has an upper bound c in the domain AB. Okay, and now we're going to see if that leads to a contradiction. And because it has an upper bound c, we're going to say let x1 be the least upper bound of S. Okay, the point at which it transitions once again from g being less than or equals to 0 to g being greater than 0. Okay, and the transition point, because g is continuous, in fact, the function specified by its first derivative equals to a continuous function is itself continuous. We have that g of x1 is equals to 0. Okay, but we also have more information because g to the right of x1 is always positive, and g to the left of x1 is negative. We have that g derivative at x1 is greater than 0. Okay. But we know what the g derivative at x1 is, and in fact we can actually evaluate it because at x1 we have g of x1 equals to 0. So substituting g of x1 equals to 0 into this expression, we find that the derivative of g at x1 is simply g of xz minus f of xz, because g of x1 is 0. Okay, and this all evaluated at x1. But from this condition up here, our assumption, we have that that is less than or equals to 0. Okay, and this cannot be. So this is a contradiction, right? We've just said from the assumption that x1 is the upper bound of s in AB, we have that g of x1 derivative is greater than 0. But our assumptions indicate that should such an x1 exist, in fact, it would be less than 0. Okay. Therefore, the assumption that there is an upper bound of S, okay, in AB is false. Okay. And therefore, S must involve the whole set AB. Okay. In other words, g of x must be less than or equal to 0 for all x in AB. Okay, so that's a statement just about first order derivatives with arbitrary functions that obey or sort of a statement that compares solution to first order derivatives if you know something about the function that defines the derivative that you're solving for. There's a corollary to this thing that's also useful a little bit later on. Let us say at some point x star in the domain AB, you have the special case where z of x star is equals to y of x star. Okay. And then what that implies is sort of retrospectively it would turn out that y of x and z of x are equals to each other not only at x star but in the whole domain to the left of x star, in other words from a to x. And there's quite a cute proof to the solution. Let's look at it. Let's change variables, okay? And we make x star the origin in a way. So let's say let x equals to x star minus xc, where xc is our new variable. And we know that c is equals to 0 at x star, and it has a maximum, or sort of has a maximum reach to x star minus a. So when c is equals to x star minus a, x is equals to a. Okay, so we're inverting the way in which we traverse the domain. And we're going to set y of x equals to tilde xc, y tilde xc. In other words, the values are the same, but the functions are functions of different variables. And z of x is equals to z tilde of xc. And we're going to try and rewrite the coordinates, or rewrite the differential equation for y and x in terms of xc. But then we must be careful, because when we take derivatives of this function y, ddy is equals to minus ddxc. Okay, so taking derivatives or primes on a y, or y of x, and a prime on a y tilde of xc are two different things. Okay, and to accommodate that, let us define new functions. So let us say f of xc y tilde is equals to minus f of x star minus xc, in other words f of x and y tilde. And we do the same thing with the g. We say that g of xc, z tilde, is equals to minus big G of x star minus xc tilde at z. Okay, and then we write the new differential equations, both of them, in terms of the new functions. And you'll see there we have y tilde prime, which is dy tilde dxc, which is equals to minus dy dx, okay, is equals to f, because the minuses cancel. Okay, and similarly, we have that z prime is equals to gxc z tilde. Okay, The initial conditions now comes from this assumption. Okay, so at c equals to 0, x is equals to x star, and we have that z tilde at 0 is equals to y tilde at 0. Okay, but we also have another feature. Okay, so that specifies the initial conditions, but we have another feature in that there's a g is always greater than or equals to f. Okay, so it's just the order reversed here, because you can use the inequality from this definition, okay, multiplied with a minus, and you get an inequality for f and g. So we have that g is always greater than or equals to f on the domain, and this is the new domain, c from 0 to x star minus a. And this now permits us to apply the CT theorem not to the variable x, but actually to the variable xc. Okay, so we have that if, because the initial condition is also satisfied with the equality, we have g greater than f, therefore z tilde is greater than or equals to y tilde. Okay, and thus, because these two have the same value, z of x is greater than or equals to y of x on the whole domain x in 0 x star, or equivalently c, sorry, in the whole domain x in a x star, or equivalently c in x star 0 to x star minus a. Okay, so this result over here comes from looking at the c equations. But we can also apply the comparison theorem directly to f and g as specified over here, which is the original problem. And if we do that, we get that y of x is greater than or equals to z of x on all of AB. But if you look at these two, you switch the order. So on the subdomain x in a x star, we have both z greater than or equals to y and y greater than or equals to z. So that can only be satisfied if y in fact is equals to z. Okay, which gives us the result that we want. Okay, so that concludes the general comparison theorems. What we're now going to do is apply them to the prefer system that we get from rewriting the Sturm-Liouville operator as a first order form. Okay, so what we're going to do is we're going to construct two differential equations with different functions p of x and q of x, and we're going to call the first equation the hat equation, and the second equation, and we're going to specify its initial conditions at a, and the second equation is just going to be the ordinary equation, so p is different, p of x is different from p of hat of x, and so this thing basically constructs the second function f. We're going to also have this initial condition theta of a is equals to theta 0, and what we're then going to do is have this first result where we've applied the comparison theorem to this system in particular, and we're going to say, suppose for theta and theta hat, q is greater than or equals to q hat. In other words, this q is greater than or equals to that one, and p is less than or equals to p hat. Okay, we have that if theta 0 is greater than or equals to theta 0 hat, okay, then theta of x is greater than or equals to theta hat of x on AB. Okay, and then the corollary we can also write, and we say if for some x star greater than a, we have that the two things are equal, then they were equal on the domain from a to x star. Okay, and the assumptions follow by simply, the assumptions we've made here on P and Q implies that F is greater than or equals to G. Okay, and we see that because this first term is greater than that one, and the second term, because of this condition, is also greater than the second term there. Therefore, f is greater than g. We have that the greater f function's initial condition is bigger than the other function's initial condition. Therefore, the function itself remains bigger than the function with a smaller velocity. Okay, so there's and then given this P2, there's another result which basically is a corollary applied specifically, that results specifically when you apply the comparison theorem to the Pfeiffer system. And what that is suppose rather than having a greater than or equal to, you have a strong inequality here on AB, then you also have a strong inequality on the solutions. In other words, the solution theta is then always greater than the solution theta hat on AB. And similarly, an equivalent result you can also get if you say let P be less than or strictly less than P hat and Q not equivalently 0. And to see how to prove that, what we're basically going to do is say, suppose the equality holds and we're going to get a contradiction. Okay, so if theta is equals to theta hat at some x star in AB, okay, then by basically P2, this result, we have that theta is equals to theta hat for all theta on A to x star. Okay, so there's a definite domain in which this equality holds. But what that means is that on A x star, this differential equation, we basically have theta hat is equals to theta, so we can subtract these two differential equations, the derivatives cancel, and we are left with this expression. And now if you look at this expression very carefully, we've assumed that Q is greater than Q hat, so this thing is positive. This is also either positive or 0. And we've also assumed that 1 over P minus 1 over P hat is also positive or 0 because of this inequality. Okay, so we basically have the sum of two positive things, and if that is equals to 0, okay, they must vanish separately. So, and if that is true, we need this thing to vanish, but because PQ is greater than Q hat, we know that sine theta must be 0, which implies that theta is equals to some constant m pi on a x star. Okay, but this contradicts the theorem that we proved in the first part of lecture, part A, namely that there is only one value at which theta is equals to m pi, and therefore our assumption that the 0 point exists between the two systems is wrong, and we must have that theta of x is greater than theta hat of x on all of A and B. Okay, so our final slide for the lecture is one of the nicest results because it starts proving statements about the zeros of the operator L that we had earlier. So it's called the Sturm comparison theorem. And what it basically does, it says, suppose we have U hat, which is a non-trivial solution of the second order operator, basically d dx, p hat du dx, sorry, du hat dx, plus q u hat equals to 0. It's a non-trivial solution, but it is a solution that has two zeros. So we're going to assume that there are 2 points, x1 and x2 in A and B, so that u's value vanishes at both those points. Okay, and then we're going to look at a second solution. Okay, and that's going to be of any solution of a second Sturm-Liouville or Sturm operator applied to U with potentially different values or different functions px and qx. And what we're going to assume, the only thing that links these two problems is this property that q is greater than or equals to q hat and p is less than or equals to p hat on, not necessarily even on the whole domain, just on the region between the two zeros of the hat equation. Okay, and the result then that starts making it possible to prove that first, I think the second lemma that we had in the previous lecture is that U vanishes at least once in this interval. Okay, so you have one solution that you know vanishes at 2 points. You have another solution that obeys this property that you can apply the comparison theorems, and you can therefore prove that U vanishes between the 2 points where the hatted solution had 2 zeros. Okay. And you can make a further statement that says if the U hat has k zeros in this interval, then U has at least k minus 1 zeros there. So we're starting to see the power of the set of sort of theorems that we've been systematically building up during this lecture. Let's now prove it. Okay, and to prove it, to describe the zeros, we only have to look at the Prefer equations. Particularly, we only have to look at theta, the theta equation. Okay, so if U is equals to 0 at x1, we know that sine of theta hat at x1 is equal to 0. And we can then say let theta hat without any loss of x1 be equals to 0. Okay. And we also know that sine of theta 2 x2 is equals to 0, and we can say therefore that theta of x2 is equals to m pi, where m is an integer but m must be greater than or equals to 1. Okay, because we know the theta equation from our first P1 result before in part A is always has got that sort of ratchet mechanism. We know that theta of x2 can definitely not be 0, it's got to be greater than that. And we might have skipped the 0, so we can say that we can describe it like this in general. Okay, so that basically gives us what we can say about the hatted equations. Now let's go and look at the initial conditions for theta. Okay, so we've said nothing about the U equation's initial conditions, so we can basically take theta to be the general initial condition, and as you know from the first slide of part A, where we discussed the Prefer substitution, we can have that theta of x1 is anywhere between 0 and pi. Okay, because it's defined by a tan. You basically, to specify the initial conditions, the only condition it has to hold is that tan of theta is made up of the initial conditions for U, and it'll always have a solution between theta and pi. Okay, so without loss, we can assume that. Okay, and when we've done that, we have the conditions for the comparison theorem on the previous slide, namely theta is greater than theta hat because theta hat is 0, or greater than or equal to theta hat because theta hat is 0. And therefore we know, and we also know that, and therefore we know that theta of x will always be greater than or equals to theta hat of x. But we know that theta, in particular, that theta at x2 will therefore be greater than or equals to theta hat at x2. But theta hat at x2 is equals to m pi. Okay, so we have a function that at point x1 is less than pi, and at point x2 is greater than or equals to pi. So somewhere between x1 and x2, theta must equal pi because theta is assumed to be continuous. In fact, is continuous because it's the solution of a first order differential equation with this with continuous functions on the right hand side. Okay, so theta is equals to pi somewhere between x1 and x2, but whenever theta is equals to pi, that means that U, which is equals to r sine theta, is equals to 0. So we've proved the first part of the equation, basically that U vanishes at least once in the interval where U hat between the two zeros of U hat. And the second part actually follows from applying the first part several times. Okay, so now if U hat has k zeros, including x1 and x2, then U has at least k minus 1 zeros in the region x1, x2. And the way we prove that is simply to apply the previous argument to each pair of zeros. Okay, and we find that it has that U has a zero between each pair of zeros of U hat. Basically resulting in this thing that it has at least k minus 1 zeros there. Note that it can sort of make a little loop, in which case it can have more than k minus 1 zeros, but it has at least k minus 1 zeros that we've proved. Okay, so this is the first indication that this operator, or the Sturm comparison theorem, basically shows that L applied to U has oscillatory solutions, okay, provided you can find a non-trivial solution U hat for which these conditions, which has oscillatory solutions. Okay, so we haven't proven that U has oscillatory solutions. We've found a mechanism of proving it. Okay, and we therefore, in order to prove it, we have to construct a valid U hat, which actually turns out to be quite easy and very useful when we try and look at these problems for complicated operators where P and Q are messy. Okay, and what it also further does, and we'll see how it does so, it allows us to estimate the number of zeros in the solutions as well. Okay, and to do that, it all comes down to constructing a very cleverly chosen U hat equation that we can manipulate and understand. And to do that, let's say let a constant P of M be equals to the maximum of P and X of AB on AB. In other words, this function that we can't, that is quite hard to find a solution for. It's very easy to find the maximum of it on the interval. And let QM be the minimum of QX on the interval AB. Okay, so we have two constants that we define that way. And what we're then going to do is to consider the comparison equation, in other words, the hatted equation, where our functions are constants, which is going to make it very easy to solve. So we're basically going to say, let P hat be equals to PM and Q hat be equals to QM. Okay, and by construction, we have that Q is greater than or equals to Q hat, which is equals to QM. And P is less than or equals to P hat, which is equals to, because we've chosen P hat to be the maximum of P. Okay, but the equation, the U hat equation, now becomes beautifully simple. Okay, it's just this thing, but P is constant, so we can move it out and divide by it because it's not zero, it's greater than zero by assumption. And what we're left to is U hat's second derivative is equals to QM over P big M of U hat, which is the harmonic equation. And in the situation that Q over P is greater than zero, okay, we can just set that equals to K squared, kappa squared. We know that this thing has oscillatory solutions. And in particular, one such solution is U hat is equals to, that has a zero at x equals to a. So we're going to put the zero right at the beginning of the domain. So a valid solution to this problem is U hat is equals to sine kappa x minus a. Okay, which makes it very, very nice. So we have a sinusoid that we know is oscillatory, and the place at which its zeros occur is dependent on kappa. So now if we want to construct a solution with k zeros in the domain AB, we know that this is only possible if you can fit in k wavelengths for this particular sinusoid, and that occurs if we have kappa of b minus a is greater than k minus 1 times pi. Okay, so if that holds true, then U hat has at least k zeros on AB. Okay, so we have full control of our U hat, and we understand its zeros, and then as a consequence, we can say for the solutions of U, the solutions of U must at least have k minus 1 zeros. Okay, so it's a very clever argument by which we've bounded the number of zeros that U has by solving an equation of constants that are constructed from the equation for used functions that enter there arbitrarily. We don't need to know the details of the functions, we only need to know their maximums. And we can already say that or we can put a lower bound on the number of zeros U has in the domain. Okay, and when we start looking at the full Sturm-Liouville eigenvalue problem, I mean, in this lecture we've just explored the oscillatory nature, we can observe that to have many zeros, Q and therefore Qm must be very large. Okay, and that is true because if Qm is large, kappa is large, okay, this condition becomes easier to satisfy. Okay, and that fact that we have many zeros with Q comes into play, and there's a reason why we've introduced lambda into the eigenvalue problem. It's a constant that we can tweak that shifts Q larger and larger and larger, while the actual functional dependence remains just hidden in Q. Okay, so the parameter lambda in the Sturm-Liouville eigenvalue problem basically makes it possible to scale the number of zeros you have for the Sturm-Liouville, for the actually oscillatory solutions. And that will illustrate the next lecture. So this concludes sort of building up the theorems that are necessary to prove the most general results for the Sturm-Liouville theorem and particularly the eigenvalue problem. I mean, in this lecture, we've just stuck to the classical second order operator and derived a whole bunch of reasonably powerful theorems that have had, since their derivation, a tremendous realm of places where they've been applied. And they are reasonably simple. It's a very clean argument to getting to them. And during the next lecture, we'll start looking at the Sturm-Liouville theorem, which includes this eigenvalue, as well as using the functions or the oscillatory of functions obtained and proving that you can expand any function f that obeys the right boundary conditions in terms of solutions to your Sturm-Liouville problem. Thank you very much. This concludes lecture 24.